Welcome everybody. Good morning. Thank you all for coming here. We are Team Wing It from Marlborough, Massachusetts. We're representing Massachusetts at this year's National Design Challenge. We're really excited to talk to you all about what we've been working on in the last few months. This is our third year as a team and our third year representing Massachusetts nationally. We're super excited to talk to you, and we've done so much work in education and learning about what this program is about, and again, we're super excited about it. So before we begin, we should talk about some of our team this year. This year is our largest team ever. We've been recruiting all around the school. We have some great people who've come in to help us, great mentors, great teachers, and great students. These are the top STEM students from our school, and they really love to work with the team, and they're all interested in pursuing STEM careers. Our team members who are with us today: Rachel Doss, Chris Ortiz, Peter Conti, Annika Lambert, Alex Sutton, Nick Delasola. And I am Ben Shepard. I am the team leader. We also have faculty advisors here with us today, Mr. Ken Hansen and Ms. Stephanie Parker. They have been instrumental in this program, and they have been so supportive of us throughout the whole thing. We're really thankful for that. We've also had really great mentors from the industry. Our first mentor, who is here with us today, actually, is John Elliott. He works in the Naval Surface Warfare Center in Virginia, and he has extensive UAV knowledge, and he has been instrumental in this project. Also, we worked with a man named Randy Holtry, who is unfortunately not able to be with us today. He works at the Marlborough, Massachusetts branch of Raytheon Corporation. He has also been very helpful in this project of ours. And so their contributions are certainly invaluable, and we can't thank them enough. Now, before we talk about the decisions we made in this project, we need to talk about what the challenge is really about. This year, the challenge revolves around something called an SUAS system, or a Small Unmanned Aircraft System. A Small Unmanned Aircraft System is a system which involves one or more airborne vehicles with a ground base and communication system. Now, these vehicles and communication systems can work together to accomplish a similar goal, and they can help each other out, and so we can do our goal most effectively. So in this challenge for this year, the challenge is to find a boy who is immobilized wearing a blue jacket somewhere in a defined search area out in New Mexico. Now, this program is specifically very difficult because there's different sectors we have to search with different amounts of trees, and this presented really unique challenges to us. Also, part of the plan this year is a business case. The business case this year stresses efficiency and cost effectiveness. We had to make trade-offs and decisions in our parts and flight pattern to make sure that we have the most efficient UAV system possible. Obviously, we need to compete with current commercial applications for UAV and search and rescue systems, else our system is not really viable. Therefore, we're really excited to talk to you about what we have chosen. First up, we're going to have Peter Conti, who's going to talk about our conceptual design.
Thanks, Ben. Over the course of this project, it was determined that multiple UAVs would be more effective in locating the target child. The first UAV was inspired by existing concepts of UAVs. It was originally conceived with a pusher propeller at the rear to propel the plane from the back, but that was scrapped later on in the design process due to complications surrounding the design of landing gear. The second UAV was based around AMA model aircraft, and it focused on limiting size and weight. The first UAV's design was based around a 6-foot cylindrical fuselage, which narrowed at the rear to reduce material, and it formed an aerodynamic cowling around the front. The wing utilized an NACA 6409 airfoil, which is an airfoil that is efficient at delivering high lift at lower speeds. This is a rendered view of our first UAV. The second UAV took inspiration from modeled aircraft. It was slightly smaller than the first UAV since it was only used to determine the actual location of the target child. Aerodynamics were not a priority due to the smaller size of the UAV. This UAV also utilized the NACA 6409 airfoil. And this is a rendered view of our second UAV. For the weight of the first plane, it was roughly 42 pounds, which is roughly 13 pounds less than the limit of 55 pounds. And the second UAV's weight was roughly 30 pounds, roughly 25 pounds less. Both UAVs had a center of gravity roughly 12 inches behind the front of the plane, which is about underneath the wing. The fuel tank was also placed underneath the wing, so that as the fuel depleted during flight, it would not offset the center of gravity and therefore unbalance the plane. Now off to Nick for aerodynamic characterization.
Thanks, Peter. In our state challenge designs, our first UAV had the NACA 2412 airfoil, and the second identification UAV had the NACA 10 airfoil. But after the national challenge added flow, we determined through the flow calculations that neither airfoil allowed the planes to stay in the air rather than take off or even cruise. So we changed both of them to the NACA 6409 airfoil. We tested these airfoils at a 10-degree angle of attack for takeoff and a 2-degree angle of attack for cruise. Not necessarily that that's the angle of attack that they would always be, but just as a test. The 10-degree angle of attack produced 176.9 pounds of lift for the first UAV, which is roughly 4 times the weight of the UAV, so it will be able to take off very easily with that amount of lift. It also calculated the drag for us, which was nice, and it gave us 4.53 pounds of drag, which isn't a lot of drag. At the 2-degree angle of attack, it produced 131.62 pounds of lift. And that's still 3 times the weight of the UAV. So we can lower that angle of attack closer to 0 to keep the balance of lift to weight equal. And then the drag at 2 degrees was also pretty low at 2.274 pounds of drag. And now over to Chris Ortiz for our sensor payload expert.
Thank you, Nick. Regarding the sensor payload, the team selected the X1000 for one UAV and the X4000 for the other UAV. Our flight plan consisted of one UAV containing the X4000 to pan a large plot of land to detect the child. Once an object of interest was detected, the UAV containing the X1000 would fly to the specified location at a lower altitude to identify the object as the child. This technique would allow the UAV containing the X4000 to continue to detect objects of interest without having to interrupt its flight pattern in order to identify an object, thus reducing the overall mission completion time. Most of the ground station equipment was mandatory for the mission's success, such as the safety pilot flight boxes and the operational pilot workstation computers. However, the choices that could be made helped decrease the price variable found in the objective function. There were 2 sensor payload workstation computers to choose from, version A and version B. Version B was chosen because it was equipped with software capable of detecting objects at a lower resolution and in a smaller time interval, as well as it eliminated the need for data analysis by informing the operator directly of the detected object. This decision would reduce the mission cost over 50 missions because software only needs to be purchased once, while the personnel of the computer eliminated needs to be paid per hour. For the trailer model, the team selected the fleet shelter model because it was equipped with 2 UAV racks, which is necessary in order to properly store the team's UAVs. Of the personnel, at least 6 individuals were required: 2 safety pilots, 2 operational pilots, 1 payload operator, and 1 maintenance range safety launch and recovery officer. In addition to this, 1 launch and recovery assistant was assigned, as well as 3 ground search personnel. Of the additional UAV components, certain equipment was necessary in order to complete the mission. This included 2 command data link UAV transceivers, 1 for each UAV, and 2 video data link UAV transmitters, 1 for each sensor payload. To communicate with the command data link UAV transceivers, 2 command data link ground UAV transceivers were required. Similarly, to communicate with the video data link UAV transmitters, 2 video data link command receivers were required. When selecting batteries, both flight pattern and estimated completion time needed to be taken into account. The team's estimated completion time was 1.86 hours. This required a battery that could last as long depending on the item being powered. The team chose to use lithium polymer batteries because of their impressive battery life and power density. For all devices, we selected 5 batteries plus an additional set that will be charged and swapped in case the need for refueling arises. Now Alex will discuss the propulsion of our section.
Thank you, Chris. The propulsion team's engine selections were aided by the estimated engine sizing requirements chart in an effort to keep the cost of each engine to a minimum, while still having enough power for easy flight. Along these lines, we decided both engines would be fueled by gasoline, rather than carrying an additional type of fuel such as blow fuel. Carrying only gas would make refueling quicker, as well as cut costs. For the primary UAV, we decided the GA55 engine from the catalog was a good fit for the weight of the aircraft. The engine is light and powerful at a low cost, all characteristics of a 2-stroke engine, compared to pricier 4-stroke ones. We strayed from the catalog with the DLE 30cc 2-stroke engine. This engine again provides the perfect performance for the smaller, lighter fixed camera UAV. fuel, 87% octane gasoline is mixed in a 30-to-1 ratio with castor oil. The octane chosen was the minimum recommended by the DLE manufacturer, but provides a fitting fuel at the lowest possible cost. Castor oil was chosen as safer and more biodegradable than synthetic oils, making it perhaps a more eco-friendly choice. Wood propellers were chosen for both UAVs. Wood props have a high strength-to-weight ratio, as well as excellent vibration dampening properties. Importantly, they are cheap enough that extras could be carried to the mission zone, and in the event of a propeller break, they could be easily replaced. This cannot be done with more expensive synthetic propellers. The pitch and diameter of the propellers chosen were to give both aircraft ample takeoff power at the cost of a little airspeed. All the design choices made by the propulsion team were to minimize cost and maximize performance. Next up is Annika with the flight plan.
Our flight pattern for the state submission consisted of 6 sectors. The first UAV would fly in a pie-shaped form, and in a pie shape, flying to the center of the area 6 times. This was to ensure that there would be no objects obscuring our vision from detecting and identifying the unborn. To adapt to the state national challenge, which has 3 zones, one with no trees, one with small trees, one with tall trees, our pattern changed to 18 concentric arcs for the first 2 zones and 19 concentric arcs for the 3rd zone. To cover for the camera footprint changing between zones 1, 2, and 3, we needed to add an additional zone to decrease the size to cover the full area. The second UAV, like the state challenge, has no set flight pattern, but instead flies directly to the coordinates given by the first UAV in order to identify the unborn. To make sure the boy is identified, the second UAV flies in a circle around the object identified in order to keep the boy within the camera footprint for the 95 seconds required to determine his identification. The first UAV will fly in this pattern as you can see here. Each line represents the flight it takes. There we go. This is the first UAV, which will fly in this pattern as you can see here. The UAV begins its ascent into zone 3 and then begins the arc pattern starting at the 250-degree mark. After completing each arc, the UAV travels into zone 3 once again to turn around and proceed back for the second arc moving outward. After completing the 18 arcs in zones 1 and 2, the UAV travels through zone 3 and completes a similar pattern moving inward for 19 arcs. This is the first UAV. These are 3D prototypes. And now Nick will discuss maneuvers.
Thanks, Annika. So the designated flight pattern of the first UAV requires the first UAV to make pretty large radius turns. However, the smallest radius turn that it has to make is the innermost arc between zones 1 and 2, which requires a bank angle of 43.42 degrees. That produces a load factor of 1.38 Gs on the wings. The assumption of the challenge was that the wings could withstand up to a load factor of 3.8. So this load factor will be withstood by the wings when in this turn. All the other arcs of the flight pattern are not as small as the arc of the innermost arc of zones 1 and 2. So all of the load factors will be less and thus will be withstood. The second UAV is mainly straight flight. It will fly directly to the coordinates and then make a turn. The turn will be 445 degrees at a bank angle of 70 degrees. The 70-degree bank angle will produce a load factor of 2.92, which is still less than the limitation of 3.8. And now over to Rachel for the business case.
So the final aspect of this challenge was to write a business plan involving our system. Listed before you are the various components involved in actually constructing our UAVs, and which is the total initial cost. And this came to slightly less than $79,000. Following initial cost, we needed to determine the amount of money it would take to actually operate our system. This includes the cost for manpower and the cost for fuel. We used the RWDC crew requirements in order to devise our personnel, and their work hours come from the time to travel, the time to set up and take down the ground station, and the time to actually operate our mission, a total of 9.86 hours. Also, the total fuel cost came to $10, including the cost for both UAVs. But since we only use 40% of our fuel during each mission flight, we only pay $44 for fuel during